Okay, so let's start. Thank you again for your patience. So we want to have a little bit of overview of complex analysis because it is so useful in every branch of physics. So last time we studied we reviewed some important theorems for holomorphic functions. And the theorem that is mostly used for evaluating contour integrals is known as Cauchy's residue theorem, or sometimes known as Cauchy's residue formula. And what it says is that, suppose that we have some region, say C, C, and in that region we have some a holomorphic function, and we have some singularities of the holomorphic functions at some points z1, z2, Zn. Now, if I take a contour and I cover that contour, sorry, this is a very ugly contour, but it's a valid contour, and which surrounds all those singularities, then the contour integral over this contour, let's call this contour gamma, of the function f of z, which is holomorphic except at the points it blows up, is going to be given by 2 pi I times sum over all the residues of the function f of z at z equals to zk. Okay, and remember that what is a residue? A residue is that if we have a singular point of the function z naught, then if I expand this, then in the expansion there is a term which is the a minus 1 term. So this is the term, this is the coefficient of the 1 over z minus z naught. And this coefficient is called the residue. Okay? So do we have any questions about this?
No, sir.
Okay, so we also talked about 2 kinds of singularities. The first one were like poles. And poles basically, were singularities where, if I had a function, if the Laurent series expansion had a finite number of singular terms, so that means that the terms which were the terms with the negative exponents, if there are like, so this should be n, a minus n minus 1, z minus z naught, z of n minus 1, ... And then, there may or may not be, there's a term a minus 1, z minus a, sorry, not a, I meant z naught, and then a0, and then non-singular terms. So if the number of non-singular term is finite, then that kind of pole, that kind of singularity is called a pole. And if in particular, if the singularity is such that the singular point has only the exponent minus 1, then that kind of pole is called a simple pole. Okay? This is a simple pole. If, for example, in this case, n is greater than 1, is the singular point has higher power than 1, then that's called I think it's called a higher order pole. Okay? So, and then of course, we talked about the essential singularity, and the essential singularity, an example would be 1 over z, which is 1 plus 1 over z plus, say, 1 over factorial of 2 z squared, ... Okay? So this is an essential singularity because if you, so for example, with the simple pole or in the multiple pole, if you suppose that my function f of z has a multiple pole, has a higher order pole, or say has an order pole at z naught, then if I multiply this function by f of z, then I get a function which is non-singular, right? So this is non-singular at z equals to z naught. But the thing about the the essential singularities is that there is no factor that like this that you can multiply it with a polynomial factor that will get rid of the singularity. Okay. So just a technical term, sometimes you will see the word meromorphic used. Meromorphic function. So a meromorphic function is a holomorphic function whose singularities are, all its singularities are on the finite part of the complex plane, okay? So it's a holomorphic function, all of whose singularities are on the finite part of the complex plane. So for example, f of z equals to 1 over z is a meromorphic function, whereas f of z minus z naught is not a meromorphic function because you can show that this has a singularity at infinity. Okay, so these are technical, just very minor stuff. So now that we have introduced the singularities, so if you want to use the Cauchy's residue theorem, we need to know how to calculate the residue. Okay, so if you have a function with a simple pole, then say f of z has a simple pole, then the way to compute the residue of f of z at z equals to z naught is very simple. You take the limit of z goes to z naught, and you multiply it by z minus z naught f of z. And with a little bit of thought, you can convince yourself this actually gives you the residue of the simple pole at z equals to z naught. Okay, because if you expand f of z, all the higher order term will go to 0 in this limit, right? So the only term that will not go to 0 is the term with the a minus. Because that term, the denominator, you're getting rid of the denominator by multiplying with this, and therefore that term is independent of z. Okay, so this is for a simple pole. But for higher order functions, for higher order poles, there's a simple formula. Suppose that my function is f of z, and it has the expansion of a to the power n minus n, z minus z naught n plus a minus n minus 1, z minus z naught n minus 1, and so on and so forth, right? So it has a pole of order n. Okay. Just 1 second. Yeah. Okay, so how do we find the residue for this kind of pole. So the residue, which is of course a minus 1, the formula for that is that you take the limit where z goes to z naught, and you divide by factorial of n minus 1 factorial. And then you have, first you multiply the function f of z by z minus z naught to the power n, right? So what does that do? That gets rid of the highest, that gets rid of the z dependence of the highest power. And then you take, and all the other terms become non-singular. And then what you do is that you take the derivative of this resulting thing by n minus 1 times, and then you basically pare it down to the a minus 1 term. And then when you take the z equals to z goes to z naught limit, all the higher order term, the finite term, they go to 0. Okay. Any questions? Okay, I will, we'll do some examples, and I might have you do some examples in the coming, this week's tutorial. Okay. And you might say, okay, what about the residue of the essential singularities? There is no formula for those. You just have to expand it and then pick out the coefficient of the 1 over z term, okay? Or 1 over z minus z naught term. Okay, any questions? So these lectures are kind of based on a set of 4 lectures that I gave at PI many years ago. So what I'll do is that I will not give you a separate lecture note for these lectures, the complex analysis lectures. Instead, what I'll do is that I will upload my typed up LaTeX lecture notes onto the Vuex. And what we are doing today and what we did yesterday, you can find it in lecture 3 and 4. And if you haven't had it, so you don't have to look at the whole of all the lecture notes, but a subset of the lecture note will cover what we're doing today. Is that all right?
Yeah. Yes.
Yeah, I just don't want to replicate work. Okay, any questions?
No, sir.
Okay, let's do an example, okay? So an example is, suppose I take this function f of z, which is, say, 1 over z squared plus a squared, where a is some complex number. So my question to you is that what are the where are the poles of this function, or where is the pole of this function, number 1, and is the pole a simple pole or a higher order pole? So
It's a simple pole.
okay, where are the poles then?
Plus minus IA.
Right, very good. So what we do is a z squared plus a squared. We know that we can write this as z plus IA times z minus IA. And therefore, f of z is, we can write this as z plus IA, z minus IA. And therefore, we see that these are the poles, I plus IA and minus IA, right? So, okay, so, well, this is the plus IA pole, and this is the minus IA pole. Okay, so how do we find the residues? Okay, so the residue of f of z at z equals to IA is equal to the limit where z goes to IA, z minus ia times f of z. So that means that this term will cancel out. So as a result, we have 1 over z plus ia, but we are taking this limit, so we get 2ia. And of course, I forgot 2 pi I here, right? So the residue at that point is pi over a. Sorry, yeah, so that's not the residue. Yeah, sorry. My bad. The residue does not have any 2 pi. That's just what we need for the theorem. Yeah, sorry. If we are going to do an integral, so that's what we need. So this is going to be 1 over 2 pi a. And the residue at the other point is going to be minus 1 over 2 pi a, okay? Right? So similarly, if I had taken the function, say f of z is 1 over a squared plus z squared, but now we have a square here, where would the poles be and what would be their order?
So second order.
Yeah, it would be the same place and it would be second order. Okay, so yeah, it's pretty simple. Any more questions? Or just like, you can just say things like, I don't understand what you're talking about.
I certainly have a bit trouble figuring out how this all connects to our quantum mechanics part.
Oh, I mean, this is a completely different subject. It just connects because, for example, we took the Fourier transform of, say, the top hat function, right? Mm-hmm. So this is the top hat function. And we found that the Fourier transform of that function is a sinh function, right? It was like something like this, right? So, and then we saw that, okay, so this is the FT, Fourier transform of each other. And then we saw that, this thing is equal to this thing, right? This is the called Percival's formula, and this is, if you normalize it, it's equal to 1. So you can do this integral very easily because it's just a top hat function. It's a trivial integral to do, but when you do this integral, you will find that it's not such a simple integral to do. And you will need, the best way to do this sort of integral is to actually use the technique of complex analysis. Now, I understand that many of you in this class haven't really done much complex analysis, so I just thought that I would take 2 lectures out and give you a brief primer on complex analysis and how to do integrals using complex analysis, okay? So yeah. This is a subject that is not going to be examined. It won't be, but I want you to know about this so that going forward, either in this class or other classes, you have some point of reference when it comes to complex analysis. You don't have to understand this 100%, but it'll help you going forward.